Are you a compulsive channel changer, able to watch 7 programs at the same time? When you change channels on a television, you are tuning in to different frequencies of electromagnetic radiation. Each frequency reaches your set as part of an electromagnetic wave. But what your television picks up is only a small portion of an entire range or spectrum of frequencies called the electromagnetic spectrum. Some of these other frequencies are picked up by radios, and some are even sensed by your body. Others are only detected by specialized instruments. Let's imagine that your television is a super receiver that could pick up all forms of electromagnetic radiation. We'll start at the low end of the spectrum, where the frequency is very low, only 60 cycles per second. 1 cycle per second is called a hertz. You can hear 60 hertz as the low hum that shows up in most amplifier equipment. The waveform at the lower left represents the electromagnetic wave. At 1,000 hertz, or 1 kilohertz, you move into radio waves used in communication. The first thing you would hear is maritime broadcasts like Coast Guard, marine operators, and pleasure craft. At 580 kilohertz, you're into the frequencies used by AM radio stations, which takes you up to 1 million hertz, or 1 megahertz. After AM radio comes shortwave, or ham radio, operated by amateurs, where you'd hear a lot of international conversations. Then it's air traffic control, followed by citizens band. Then, at around 54 megahertz, channels 2 to 4 of commercial television.
$5,000.
If your antenna was big enough, you could pick up radio signals from space before you get to channel 5 of television. Right after channel 6 at 88 megahertz, you could pick up FM radio broadcasts. Then military and satellite communication. At 400 megahertz, you could tune into the space shuttle before reaching the UHF television channels of 14 to 69. Microwaves, radar. Then you get into the very high frequency radio signals, the gigahertz, or billions of cycles per second. Beyond this, scientists listen to exploding stars, spinning black holes, and other bizarre objects in the universe. From this point, there are no prefixes such as kilo, mega, or giga for the frequency. Instead, the frequency is given in scientific notation. From here, we simply count powers of 10. At 10 to the 13th, you might get a surprise because your television would feel hot. Heat is infrared radiation. For a very small segment of the dial, about 10 to the 15th hertz, you would briefly see a flash of color, visible light. All the colors of the rainbow are in this one section, the only part of the spectrum our eyes can detect. But there's more. At 10 to the 17th hertz are X-rays, energetic enough to pass through materials, like your body. Then gamma rays, which can pass through steel, and high-energy cosmic rays beyond 10 to the 20th hertz. This is the entire electromagnetic spectrum, and all of it is electromagnetic radiation. Because electromagnetic radiation is in the form of a wave, its frequency, wavelength, and speed obey the same rules we saw in our unit on waves and vibrations. But in this case, all electromagnetic waves travel at the same speed, the speed of light in space or close to it in air. That means if the frequency goes up, the wavelength shortens, and if the frequency goes down, the wavelength lengthens. The low-frequency radio waves are thousands of meters long. For simple one-way voice communication, they suit the purpose. Radio and television signals contain much more information, so they need higher frequencies. These waves range from the length of your school to the width of your shoulders. Visible light is slightly shorter than house dust, and super high-frequency gamma and cosmic rays are so short they would fit inside a single atom. The other effect of changing frequency is the effect on energy. You will see this equation in your text. The H is called Planck's constant. It's a number that doesn't change. So if the frequency increases, the energy goes up. If the frequency decreases, the energy goes down. That's why high-frequency X-rays can penetrate steel. They have extremely high energy. So they can be used to inspect the quality of steel manufacture. The remarkable thing about all of these wave energy types is that they're all the same thing, electromagnetic radiation. The only difference between light and radio waves, between heat and X-rays, is the frequency and the wavelength of the wave. It's a good thing our eyes can only see one very small part of the electromagnetic spectrum. If we could see all of it, the skies would be ablaze with the flickering of the millions of conversations, programs, data transmissions, and bombardments from space that constantly pass through our skies. In the same way that light will pass through some materials like glass, but not through your hand, other forms of electromagnetic radiation can do the same thing with other materials. What you're seeing is still a shadow, except the source of radiation was X-rays instead of visible light. Rex Harmon explains the process further.
X-ray is a rather simple process where you produce X radiation electronically in the cylinder up here, project that down through the patient to a film which is under the patient. The X-ray that gets attenuated by the bone in the patient then casts a shadow onto the film, which then creates the image. It's a lot like a camera, in that you end up with a picture, but the film is under the patient instead of in the camera. Now, computerized tomography takes the same principles and applies them in a more sophisticated way. The X-ray is again projected through the patient, but as it rotates around, as the tube rotates around the patient, and what you get as a result of the computer manipulating that image is a cross-sectional, a slice through the patient that shows the anatomy inside that slice. One of the advantages being that you can see a lot of soft tissue. You can see the brain inside the bone of the skull, for example, whereas with X-ray alone, you'd be able to just see the skull.
Electromagnetic radiation, like all radiation, is dangerous if dosages are too high. That's why the number of X-rays you can have is limited and why the operators have to be shielded.
Of course, when you use radiation in the workplace, it's important to protect yourself as much as possible. Typically, we will leave the room when we make an exposure, but sometimes that's not possible. So we take extra steps to protect the vital organs of our body. The organs that are most sensitive to X radiation are those that have the most cellular activity. Of course, the reproductive organs are the most active organs, so they need the most protection. Next to that, the thyroid is a active organ, and we have special thyroid collars that we can wear. The lenses in the eye are susceptible to a number of problems, cataracts for example, and we have leaded glasses that we can wear. And finally, for when we have to actually put our hands into the X-ray beam, we have leaded gloves that we can wear. So, managed to get 2 left-handed gloves, but that's no problem.